or spheres. And yeah, this is our last lesson for geometry. Ooh. Okay, so before we get started, just a reminder, remember your final major grade will be deciding between a test or a project. All right, so remember the project is going to be dealing with composites, and a few questions, I believe, on the slide will have stuff about like cross sections. There's other stuff too. Oh, like axis of rotation and all that fun stuff. So, um, yeah, if you have any questions, let me know. Remember, you have to decide by the 17th for A day, 18th for B day. So that way you can take your test on the 20th and the 21st, okay? But pretty much the project and the test, right, they're both due on the same day. So tests and projects on the 20th for the A day. For B day, it's the 21st. But yeah, that's pretty exciting. All right, so let's go ahead and let's dive down into the last lesson. OMG. Okay, why is there a mouse right there? Oh no, that's my Mac mouse. Okay. Um, so today's lesson is really not that bad at all. It's pretty straightforward. So with surface area, all right, what we're looking at is just taking the area of a circle and just multiply it by 4. That is all. So area of circle multiplied by 4. So let's go ahead and let's get started on an example. And why can't I not find a pen all of a sudden? Okay, we'll do this one. All right. So let's go ahead and let's look at this. So, an A, all right, number one, an A, it tells me if you see like this whole line right here, it's letting you know, hey, the diameter is that number. So my diameter is 40, all right? But remember, when we take the area of a circle, we just want radius. So my radius is just going to be half of that, 20. All right, so to find the area for this guy, and there's no lateral, it's total with these guys. All right. So all I'm going to do is do 4 times pi, and then my radius is 20, and then square. All right. So when I clean that up, right, I should get, so 20 times 20 gives me 400, and 400 times 4 gives me 1600 pi, right? So if I'm saying, hey, leave it in terms of pi, this is what I want to see. But if I ask you to round to the nearest, like hundredth or whatever, then yeah, definitely calculate pi into there. So let's go ahead and let's do that. So I have 1600 pi, and then boom. So my total, all right, you can say 1600 pi, or if I ask you to round to the nearest hundredth, 5026.55 feet square. So once again, this is in terms of pi, this is rounding. All right. Now, what happens if they actually give you the circumference, okay, and I want you to find the total surface area of your sphere? So, remember your circumference is 2 pi r, right? And here they tell me the circumference is 6 pi, okay? Well, I need my radius, all right, in order to find the total surface area. So all I need to do is divide by 2 pi on both sides, and that gives me the radius, all right? So when that happens, I should get that the radius is 3, and then boom, I can go from there, right? So once again, your total surface area is just the area of your circle times 4, right? So pi r squared, and then times 4, right? So 3 times 3 gives me 9, and then 9 times 4 gives me 36 pi, okay? And that's in terms of pi. But if I want you to round to the nearest, what is it? The nearest, we'll do hundredth again. So 36 times pi. I should get 113 point, Yeah. It's going to be like 0.9 point, or like 7, but that knocks it up to 0.1. Boom. Awesome. Okay. If you're still confused on that, just rewatch the video. It just takes practice. That's all. All right. Let's look at number 2. So let's say, hey, I want to find a part of my sphere, which is the radius, and they give me the actual surface area. So the total surface area is 30 pi, okay? Well, we already know that our total surface area, the general formula, is just 4 times pi r squared. So all I want to do is just isolate r, or just get r by itself. So first thing we can do is divide by 4 and pi on both sides. Okay, that cancels out the pi. And then 30 divided by 4 gives us roughly 7.5. But that's still radius squared. So the opposite of squaring, all right, is just taking the square root on both sides. So if I take the square root of 7.5, I get roughly the radius being 2.74 meters. And then boom. That's it. Hope we're all doing all right. All right. So last little section. Let's talk about, yeah, let's talk about volume. Pretty straightforward, but I thought I'd just make life a little bit more entertaining. I found this little video. So we talked about volume last class with cones and cylinders and all that fun stuff. Now, if you look at your notes, the volume for a sphere is actually 4/3, okay? And then the radius to the third power, because volume is talking about 3 dimensions. Boom, so r, and then times pi, because it's dealing with a circle, so we got to have pi in there. Now, let's see what happens. Gosh, there's a fly in this video. So, she's acting like this is magic. All right. So what she's going to do is show that, hey, with the cylinder, okay, they all have the same radius with the cone and the sphere. So we talked about, hey, the cone is just 1/3, all right? So it's base, the area of your base times the height, but it was just divided by 3. And with our cylinder, all right, it was just our base times our height. So if we look, if you notice, I'm going to pause right there. The cone, all right, oops. The volume of it is just actually just 1/3 of the cylinder. So that's why we divide by 3 when we're taking the volume for a cone or a pyramid, because a pyramid is the same thing but with a prism, right? Now let's look at what happens when you have the cylinder versus the sphere. All right. I love how she's like showing this off. And the blue like reminds me of ocean water at Sonic. If you have ocean water, it's amazing. If you don't like ocean water, don't talk to me. Just kidding. I love y'all. All right. So she's pouring it, and then boom, we keep going. All right. So if you notice, it actually hits 2/3. All right. But if we were to continue to fill it up, all right, what would happen is we would have 4/3, all right? It would overflow. So if we did 2 of these, all right, technically it would hit 4/3, all right? So that's the reason why it is what it is. Or if you could think about it this way, we can actually take the sphere and fill it up with 1 cone, right? And that gives us a whole cylinder. But that's why they got the formulas how they got them, is because of how much you can fill from a cylinder to a cone, how much you would need in order to get there, right? All right, let's go ahead and let's calculate volume. So when we're looking at volume, once again, all we're doing is doing 4/3 times pi times our radius to the 3rd power, because with volume, we are taking everything to the 3rd power. So our units are cubed. Now, let's go ahead and let's find the volume. So they let us know for this particular guy, we have a diameter of 3. So if it's ever in the middle, that lets you know the diameter. So we need our radius though. So 3 divided by 2, all right, it's just 1.5. So that's our radius. Okay. So with the volume, we just do 4/3, okay, times pi times 1.5 to the 3rd power, all right? And you can actually put this all in your calculator, and I'm going to do that. So I'm going to clear that out. So I have 4/3, okay, times pi, and I have 1.5, and I'm going to use the caret key to the 3rd power, and then boom. So my volume for this particular sphere, all right, is just 14.14 because I'm going to round it to the nearest hundredth, right? So it's roughly 14.14. And then when I do my units, it's going to be to the 3rd power because we're saying, hey, it's going to be cubed. And boom. That's pretty much it. All right. And then I'll do one more of these for y'all because I want to make sure y'all know how to take the cube root of something. So let's say, hey, I know the volume, but I need to find the radius. Okay, so let's say my volume for my sphere, right, is 144 pi. Right, so what we need to do is go ahead and set up the general formula for our volume, which is just 4/3 pi in r to the 3rd power, because this is what I'm trying to find. Same gist, all right? We want to get r by itself, and I know all of this is going to equal to 144. So once again, let's go ahead and let's try to get pi, not pi. Oh wait, there's a pi right there. There is a pi, sorry. So once again, I want to get r by itself. So what I'm going to do is I need to cancel out this 4/3. So we need to take the reciprocal of this. So I'm going to flip. So think about, we need to multiply by 3 on both sides, but we also need to divide by 4 on both sides. So that is taking the reciprocal. All right, so this cancels out, right? Also too, my pi, if I divide pi on both sides, they're going to cancel out as well because I have pi on both sides. So now I'm left with r to the 3rd power. And let's go ahead and let's multiply 3/4 with 144. So 144 times 3/4, and I get 108. All right, so the next thing we need to do is get r by itself. It's pretty much the same thing. So if we had it squared, we would take the square root, but this is the cube. So we just take the cube root. Okay, so I'm going to take the cube root, so make sure you put that 3 in front because I'm trying to get a single r by itself. If you're wondering how to use the cube root on your calculator, it's not too bad at all. So if you go to the math button, and if you go down to number 4 where it says cube root, you just click on that, and then boom, you just enter the number that you need on the inside. So 108, and then there we go. So my radius is going to be roughly 4.76, right? So my radius is going to be 4.76, and then centimeters, and then boom. That's it. If you have any questions on this, please feel free to pause, rewind, because it is here for you. All right, let's move on to the next page. I'm going to make this simple and brief as much as I can. All right. So with this, all right, oh, okay, yeah. So when you're talking about dimensional change with your sphere, all right, it's pretty straightforward, okay? You only technically have your radius to deal with. So when you're looking at the volume, all right, for this particular shape, what you're going to do is take that scale factor and just take it to the third power. So for example, if we're doubling the radius, okay, my scale factor is 2, and they're saying, hey, what would happen to the new volume, right? Well, all you do is say, hey, your new volume, all right, is going to be, and if you take this to the cube, okay, so 2 times 2 times 2 gives me 8. So it lets me know, hey, the new volume is going to be 8 times larger than the original. So all we're doing is taking our scale factor and we're cubing it. So for example, what happens if you were to make your radius, 5 times bigger, right? Automatically we think, well, the volume's going to multiply by 5. No, because we do radius times radius times radius, so that's 5 times 5 times 5, because we just take the scale factor and we cube it. So our new volume, right, so 5 cubed is 125, right? So it's going to be 125 times larger, right? Now, with surface area, it's the same gist, okay? So remember, surface area, we are taking units squared, so we're doing the same thing with our scale factor. We're just squaring the scale factor, all right? So if we were to double the radius, all right, well, think about it, we just have r squared, so therefore we're just squaring our scale factor. So if we're doubling our radius, the surface area, all right, is going to be 4 times larger than the original. And same thing if we were to multiply by 5, all right? If we were to make the radius 5 times larger, so what happens to the surface area, right? It's going to be 25 times larger because all we did was square our scale factor. We good? I don't know because I'm not there. All right. Let's talk about Euclidean and spherical geometry. So Euclidean is something we kind of been looking at as more two-dimensional shape, and Euclidean was kind of focusing on, what if you have a point? All right, then you have so many freaking different lines that go through that point, all right? But with spherical, I'm going to show you this fancy boy that I had in my classroom for a little while. Spherical is, I think you may have seen these like planetarian kind of things, is not looking really at straight lines, but looking at different types of circles going forever and ever and ever. Isn't that cool? Oh, there we go. So you may have seen this like on Game of Thrones and all that, and probably in observatories and all that fun stuff. Anyways, so this is what spherical geometry is kind of looking at. It looks very complex, I agree. But let's kind of look at maybe number 9 on your notes to kind of look at this real quick. So number 9, they're just asking us if this is true or false, all right? So with a parallel postulate, okay, if there's a line and a point not on the line, then there's exactly one line that goes through the point and it's parallel. So you're like, what the heck just happens? Well, the key word is just saying, hey, there's lines that are parallel in spherical geometry. So let's just kind of look at this. Remember, parallel lines means lines that never intersect. So if I'm looking at this guy right here, okay, and I'm to mess around with this, boom, boom, boom. Well, if you look, all these lines technically are intersecting. So that's not true with spherical geometry because all these lines are crisscrossing each other. And technically they're not lines, they're circles. So that's a big false. Because parallel lines don't exist. Now, they do exist in Euclidean because we talked about that before. And that was a couple of things that we learned at the beginning of the year. But now I'm twisting your brain saying, now at the end of the year, there's no parallel lines. Just kidding. Just in spherical, if you're looking at like globes and all that fun stuff. So think about your longitude and latitude lines, they all kind of intersect at one point. So that's what spherical geometry is kind of looking at. Now, if we're looking at perpendicular postulate, so the key word is just perpendicular, all right? So if we were to look at that, they're saying, hey, if there's a line and a point that are not on the same line, okay, then there's exactly one point that goes through the given perpendicular point. So all they're saying is, in simple terms, you got a line, and then when they hit, they create a perpendicular line. Well, let's look at that in spherical geometry. Well, yeah, you can create perpendicular lines, but if you're looking, technically there's not really that many. I mean, that's not necessarily true, because when they're saying true and false, they're talking about like 100% true. But in that case, this is not 100% true, because if you're noticing when adjusting some of these, so yeah, that may look perpendicular, but if you notice more lines, that's not perpendicular. Or let's do the bigger and the smaller. Let's do this. Like right here, I'm looking at this line right here and this line right here. I just created two lines, or not even lines, they're circles anyways, and they're not perpendicular with each other. All right, so technically that's not 100% true, so therefore this last guy is going to be false. Right. So the biggest thing about spherical is, hey, there's no parallel lines, and because they all intersect, and it's possible, all right, not to have perpendicular lines. That is it. Okay.